So our next session is a panel discussion on query understanding, and I'm very happy to welcome the panelists. I want to introduce the host, first of all, and the person who has suggested this panel, and that's Daniel Tunkelang. I think the name might ring a bell for many of you. Daniel has been a search consultant for many years. I think his name connects with many big brands like Apple, eBay, even Zoom, Etsy. And he's been one of the founding employees of Endeca. And at that time, he also wrote his book on faceted search and probably many other things. But these days, he has a strong focus, I would say, that's my perception, on query understanding. And yeah, I just want to hand over to him to start the panel.
Thank you, Rene. It's my pleasure to host this panel on better search to query understanding. And I think I can safely say I'm the world's leading advocate for query understanding, or at least the loudest one. And I'm clearly biased, but I feel that too much of the work on e-commerce search is focused on ranking. And let's face it, we're using increasingly sophisticated machine learning systems to do it. They do improve relevance and conversion. But a lot of the premise of this panel is that focusing on ranking is premature if the search engine does not understand the query. So it's my pleasure to host this panel, and I hope you'll all come away not only with a deeper appreciation of the role that query understanding can play in your search stacks, but also practical ideas that you can apply in the immediate future. So with that, I will introduce the three speakers in today's panel who will touch on various aspects of query understanding. The first will be Andreia Schütt, who's a data scientist on Auto's search team. And she's currently working on bringing Auto's first learning to rank model into production. She'll talk about understanding queries by analyzing user interaction and specifically through the use of human judgments. The second speaker will be Aritra Mandal, whom I've had the pleasure of working with personally at eBay, where he's an applied researcher. And his work focuses on improving eBay's understanding of search queries, and he will present ways to use AI to understand search intent with practical methods to implement query categorization and recognize query equivalence. And the third is Dominic Bessler, who is a search product manager at Digitech Galaxis. He loves solving customer problems with a focus on the overall conversation with the user, and will present a case study on using Autocomplete to help users formulate better queries. Each of the presentations will be about 20 minutes, and we will save questions for the end, because afterwards we'll have plenty of time for questions and for discussion. And I should say, all three of these companies are hiring. With that, I will hand it over to Andreia. Thank you. Take it away.
Thanks, Daniel. And thanks, Rene, for introducing us as well. I hope you can see my screen. Daniel's nodding. Very good. All right. Yeah, thanks for having us. And I'm going to be the first one in this user and query understanding panel. And I'm actually going to talk about understanding queries by analyzing user interaction data. And as you can see by the subtitle, it's about judgments as a gold standard. And maybe those of you, I think there are a few that were at Berlin Buzzwords this year, might recognize some of the contents. I hope you don't doze off, since there are some new aspects to what I'm going to tell you, in addition to what I talked about at the Buzzwords with my colleague. So, I can't, hang on, I need to find the navigation, like that. So I'm Andreia, I'm a data scientist in the search team of Auto.de. And maybe two sentences about Auto, since I don't know if every one of you knows it. We are a large online shop in Germany with around 1.6 million visits per day, and we have up to 10 orders per second. We are a full range trader, and we are currently expanding the business model to become a platform selling not only auto retailer products, but also products from many other sellers. As I say, my team is the search team at Auto.de, and I've brought some key facts about our search. So we have around 1.5 million search queries per day. And on peak days, those go up to almost 5 million search queries. They split up in around 40 million unique search terms in 2020, and overall we had around 600 million search queries in 2020. Now that you know a little bit about Otto, I come to the point of my talk. So judgments as a base for query understanding. You might be wondering, what do judgments have to do with query understanding? What does query understanding have to do with judgments? So usually if people think about query understanding, they think about NLP and text mining and computer linguistics. But actually, in my opinion, that is only one part of query understanding. So of course, you probably need some text mining methods to understand a query, but there are so many other aspects of query understanding. First of all, there is the intent behind a query. So understanding what the goal or the motivation behind an issued query is for me a little bit a different aspect of query understanding than just understanding what the text means that the user issued. The second part is understanding the user as well, because every user is a bit different. So if I issue a query, I'm aiming for something different than if Daniel is searching for shoes, for example. The next part is there's also an intent during a session. So understanding a query is also dependent on the context that the query was searched in and the state of the session that I'm as a user in at the current moment. And last but not least, it's all about what are the desired products and what is the results that the user wants to see when he or she is searching for something. So what do judgments have to do with query understanding? For me, they have a lot to do with query understanding, and they are actually applicable in many use cases. But I will come to that point a little bit later. And first of all, talk a bit about where do we get the judgments from? So how do we estimate relevance? And a common approach in data science is actually doing crowdsourcing, asking experts, having a labeling day once a week with a team where everybody has to put on some labels on the data you use to train your models. And then you show them the products or some rankings, and they need to say, oh, that's relevant, that isn't, or this is the perfect ranking for me. Actually, in e-commerce, I think we already heard a bit about it. It's a little bit different because you can understand the topicality of products from those handcrafted labels, but it differs from the relevance given a shopping intent. So in a shopping condition, there are different aspects that come into play if you want to measure relevance. Because for me, as I said, if I'm looking for a shoe and Daniel is looking for a shoe, we're probably aiming for different things. And there's also the seasonality. In the winter, it's a different shoe than in the summer. And trends play a big role in what is relevant to a customer at a certain point in time. So the relevancy is quite different, and also the products that are evaluated are quickly outdated. So this is why we as a team decided to use implicit feedback from customer logs and use the big data that we have to estimate what relevance is for a customer. So that was the first decision, but then the next one is which part of the big data we have do we use to define relevance. So most of you will be familiar with the customer funnel that we have in e-commerce. There are many people viewing search result pages. There are also a lot of people clicking on products, and that's what is usually used to define relevance for customers and also to train the models for a search result page. But then there's more relevancy signals in the customer funnel. So if customers add a product to their cart, they order it, and in the end they keep the product and they are happy with the product they got. That is actually the most reliable signal for relevance that we can get. So that is actually what we are aiming for in e-commerce. And this is why the deeper in the funnel we go, the more reliable the data we get is. But on the other hand, we only have very little data there. So the higher in the funnel we are, the more data we have, and also the proximity to the search event grows. And this is why we, as I think a lot of people in the industry, did use clicks as the basis for our judgment calculation. And the assumption was, okay, if we increase the number of clicks, it will certainly carry through the funnel. And in the end, we will also increase conversions and orders and all that stuff. So here is how we implemented it in detail. We calculated the click probability from the ratio of clicks per view of a product. And as you can see in the example, that is very dependent on the number of observations you have for each data point. This is why we, as an addition, used a Bayesian probability approach with a beta distribution to estimate a better approximation of the click probability. And it works in a way that you assume a mean click probability for each product for a query, and with each observation you get for that product, it moves, the real click probability moves away from this mean value, and you get higher or lower click probabilities based on if you collect more clicks or if you collect more no clicks or solely views. And then if we talk about user judgments, probably all of you know the position bias. So if there are products at prominent positions, they always tend to be clicked more, even though they might not be more relevant. And I think, so we also heard that in the talk before, you can use inverse propensity or probability weighting to overcome that and apply a position debiasing, and that's actually what we are also doing in our data. And now we come to the important question. So what can we use the judgments for? And actually, coming back to judgments are applicable in many use cases, I think you will also see if you try to find it, there will be judgments in each talk I think you will be hearing today. So you usually somehow need to understand what are the relevant products for a customer given a query. And therefore, judgments are applicable in many use cases. So for example, you can try to understand the query intent from judgment data. So you can try to understand if a query has, for example, a specific assortment as a goal, and then try to get that assortment based on knowing which products are relevant for that query and which are not. Actually, we also did a POC on that in our team, and it really looked very promising. If you look at queries or at a different level of classification for queries, you could also try to determine the current target of the user in his or her session or in his or her search journey. So the person could be searching for a specific product, or look for a major item that, like a new laptop that they need to do a lot of research on, and spend a lot of time making that decision. Or if the query aims for an everyday item where you actually don't care which brand it is or what the color is, you just need, I don't know, new tissues. So you don't really care a lot about all the additional information. They just need to be cheap and available. Yeah, and so on. So I think we can extend that list a little longer. And last but not least, you can also, of course, use the judgments to train a learning to rank model. And I know that Daniel introduced this panel by saying tuning the ranking too much is a bit premature if you don't really understand the query first. But we in our team currently don't have any model for ranking, but we have a lot of handcrafted ranking functions. And since we are growing a lot and becoming the marketplace with increasing number of products and assortments, the current search management basically is not scalable. And it's also fit to certain contexts and search result groups, and those are all manually defined. And we actually need to look for something that generalizes over many different assortments. Another aspect why we a neat LTR is that we are not only responsible for the search result page, where you have a query and try to understand that also with text mining methods. We are also responsible for the product pages that you can reach through navigating over categories. And in those cases, you don't even have a query that you can try to understand, but you only have like a group of products where you have to know still what the user intent behind it is and what the relevant products are in that group of products. And lastly, we wanted to start with something that is clearly defined and measurable, and we could easily do an ONNX on those and iterate on it. So before we started with implementing that LTR model, we just wanted to make sure that our definition of judgments that I talked about, where you saw we have like a lot of parameters that you could tweak, that one really matches the user's intent. And I mean, we were pretty sure though, but because it's the industry standard and we just wanted to double check, you know, to be absolutely certain that we don't train our model with bullshit. So, but then, I mean, yeah, so we wanted to make sure that we do things right. And this is why we designed an experiment to test how the judgments actually work, if they are presented to the customer, and if that really is like the gold standard of a ranking that a customer is looking for. And actually, we are quite lucky that we did that, because our first implementations for those judgments did not really meet the customer's expectations. And we are currently in the 5th iteration of trying to find a good definition of the judgments. And we are right now getting closer to becoming positive in our A/B tests. So, and this is also what I want to conclude my talk with. So I want to show you some learnings from these experiments we conducted and what we learned about query understanding from those. So first of all, we learned that availability matters a lot. So if you think about, I mean, right now here it is raining like hell, but maybe wherever you are, the sun is shining and you're thinking about going to the beach on the weekend and you're looking for sunscreen at otto.de, of course. And then you get a list of products, and maybe the first one is for kids, you don't need it, and the second one doesn't have enough protection. So you click on the third product. It looks good, it isn't that expensive, but then you see, okay, I could get it in 4 weeks. So, I mean, and you realize you only see this now. So it means you have to go back and click on every product that you find interesting to find out if you can get it until the weekend or not. And that really makes you feel very sad, actually. So this showed us availability matters a lot for the relevance of a product. But on the other hand, if I'm looking for a new couch, I don't really care if the couch arrives in 7 weeks or in 11 weeks or in 2 weeks. I care about the style, and I care about the material and the color and how the material feels like and all those other things that are not related to availability. And what this availability matter showed us as well, or in addition to that availability is important, is that the judgments you use for calculating relevance of a product can only represent what is seen by the user at that point where you collect the signal. So if you use clicks as a relevance signal, you can only measure the relevance of a product given the information you see on the search result page. Then if I click on the article page, I get more information, and it might be information changing the relevance of the product for the query that I issued. So this is something we had to learn, and that I think one has to keep in mind when implementing judgments. And as a final thing, we also learned that clicks are a good relevance signal for some queries. So if you look, for example, for a new carpet for your bathroom, you probably only care about the size and the color and maybe the material, but that's almost everything is displayed on the search result page. On the other hand, if you look for a new laptop, you probably need more information than what is shown on the search result page. You click on many products and you compare them and you read all the detailed descriptions. And then in the end, you make a very sophisticated decision on which laptop to buy. So yeah, I hope I could convince you that judgments have a lot to do with query understanding. And for us, what comes next is first of all, understand which judgments really represent the user's needs. So with which gold standard can we represent the relevance of a product for the customer? And we want to use different user signals. So for example, the add to carts or the orders, but we also think about playing around with involvement with the search result page or the article page to discover how relevant a product is. And then we also want to add, like as an add-on, qualitative feedbacks in our experiments to better understand which specific queries perform good or bad and why they do so. Then of course, if we found the right judgments, we want to use them to train our learning to rank model. And we currently are forming a query understanding team in our search team, and we might even use the judgments for query understanding then to do query segmentation, to improve selection through automatic filter application and or through query categorization. Yes, and with that, I come to the last slide that Daniel already spoiled kind of. So we are looking for people for our search team. So if any of what I talked about sounds interesting to you, you can go to auto.de/jobs and have a look around, search for search, and you can see all the open positions, but you can also just send us an email and we can talk about it. So thanks for your attention, and I'm very much looking forward to your questions and discussing query understanding with you.
Thank you, Andrea. Very nice talk. And please, as I said, everyone who has questions, we will do them after all three panelists. So feel free to put them in the chat. And we'll also have opportunities for even the panelists to ask each other questions or have questions if the rest of you don't come up with enough. So with that, I'd like to introduce our second panelist, Aritra. So he's going to talk about query understanding for categorization and query equivalence.
Yeah, hello, hi. So let me get it the slideshow. So today, thank you, Daniel, for the introduction. Thank you, Rene, for the opportunity to speak here. But yeah, let's start with the presentation. So today I will be going over an example of running query understanding query intent space using AI. So a brief discussion about myself. I'm Aritra. I'm an applied researcher at the search team in eBay. So with that, let's go on to today's agenda. So I'll go over a brief description of what query understanding is and go over two use cases where we use query understanding to extract search intent using AI. And they would be query categorization and query equivalence and similarity. As you'll see later in the discussion, these two are chosen for very specific reasons. So to begin with, we will go over a brief description of what we mean by query understanding. So query understanding can be summarized as the process of or task of inferring a set of intents for a query keyword once it is entered into the search bar. This generally happens the first thing in the search stack before even retrieval or ranking happens, because this has impact on retrieval and ranking. It's not only useful for retrieval and ranking, it also makes other decisions like the page layouts, the facets you saw on the page, the navigational aspects of the page. With that, we will also show what kind of query intents represent. So there, like the query intent can be thought of as a spectrum. So on the one end, we have coarse-grained intents, which basically rely on broad categorization of queries or classification of queries. So these will put queries in a bigger bucket as such. That's the part which focuses on the coarse-grained query intents, and the fine-grained ones are like entity extraction or drawing relationship between entities and query equivalence. For this talk, we will be going over query categorization, which is on the extreme coarse-grained side of things, and the other part that we will go over is the query equivalence, which is on the extreme fine-grained side of things. So query categorization is basically the task of inferring the category of a query. As we all know that in e-commerce, each item is basically it has a category. The inventory is always categorized. There is nothing that lies outside the category structure. So the task is to basically given a query keyword, inferring the most appropriate category from which we could draw the items from. As we'll see, this has a lot of benefits. It has relevance benefits, first of all. So it will, using a category based recall basis, will always remove accessory pollution. So whenever you do a query on the site, it will bring only the items from the relevant category and remove all results which are not from the expected category. This might not be a lot of benefit when we are sorting it by relevance, because the relevance, whether it's a rule-based thing or an MLR thing, it will take care of putting the most relevant results on the top. But then there are other sort types, especially for sites like eBay, where we do auctions and also price-based sorts. Generally, if your recall filtering will take care of removing all the unwanted results when this type of sorts are also engaged. Other than that, using query categorization also makes it easy for making layout choices, like which aspects to show, what kind of filters to show on the site, what kind of price filters to show, and even on how to represent the items on the page, whether we use a gallery view, a list view, or depending, because each category has a certain type of facet which is more suitable than the other. So identifying categories for a query, although it's a very broad classification of the query, has some advantages. So we'll go over how we can go over a basic task of doing this. As we will start with the training data for like any other machine learning task. So first, how would we gather the training data? So the process is very simple. Each item has a category attached with it. And for a set of queries, there will always be a set of queries on the site which have very high engagement as compared to the most of the other queries on the site. So it always follows in most of the e-commerce, it always follows a long tail structure. So we'll pick the queries which have very high engagements and get all the products for this query. And then from these products, we will get the categories for the query. Once we have this category, we will use the category hierarchy that we have on the site on which the products were listed to find the most appropriate category such that it meets the demand for all of these queries. And once we have that category, that's the label for this classification task. So it's basically a multi-label classification task at that point. And then we are free to use any state-of-the-art classification task like fasttext, BERT, and any other classification model. We can even come up with our own. And once we have this model, we can use this to predict the category for any query on the site, whether we have demand for it or not, and then use that for all of the previous tasks that we referred for categorization. The only thing that would be a little tricky here would be to train the model such that it's fast enough for an online traffic. Like that will depend from how much traffic you face, but it will generally the size of the model impacts that. So there is a trade-off between the accuracy and the capacity of the model and the online inference engine. So that was about query categorization. Let's now go to the other end of the spectrum where we extract intent-based similarity. So intent-based similarity is basically saying two queries have the same intent, but are represented differently when they are typed into a set of keywords. A very trivial example would be what I have on the screen. Men's shoes equal to shoes for men. Yeah, their intents are clearly the same. And when this intent space could be made infinitely more complex by introducing facts like session-based parameters and everything else, like what kind of a season it is, what kind of person he is, a male, female, everything, it can impact this intent space. But we'll stick to only the query part of it for this talk. So why would we do this? Sure, we can map one intent to another. What would be the benefit of classifying all different kinds of queries which have the same intent into a same space? One of them would be to, if we can find a set of queries which mean the same thing, then we can always map a poorly performing query to a much better performing query. So what I mean by poorly performing query is a query which is not optimized for the current search engine. It represents the same intent from the user side, but it's just not performing how we expect it to perform in the site, because maybe the site is not optimized for that query. In that case, we can use the optimized query for the site, which has the same intent, and render the page for the user. And how we use this definition of similarity can also be relaxed a little bit, as you will see in later slides, that do recoveries. For example, if you don't have items for a query, we can bring in more items for this query or similar items for this query using this definition of intent, right? It would be a slight relaxation, but how far we go, we can control that based on the user's needs. As with any canonicalization of query, like because this is ultimately canonicalizing at the intent space, we can, each query which constitute one set of intent can always share their demand signals or ranking signals with each other for better ranking and analysis. And in general, the string signals become stronger when you aggregate them for a lot more queries than a single query. So now that we have stated the advantages, let's see how we can go about doing the tasks. There are two ways we can do query similarity. One of them would be to do surface-based similarity. So surface-based similarity is easy. So it's like just syntactic similarities. These would be minor transformations of the query text itself to reach from one version of the query to another. They could include stemming, word reorder, compounding, noise word removal, one or all of them basically together to come up with the other version of the query. A trivial example was what was in the first slide, or even the one that was here, which is men's watch to wristwatches for men, which basically has all the transformations that I have mentioned above. The other more interesting one is basically using the post search behavior. So which is seeing how the result set of two queries are similar among between two queries, and using this measure of similarity to define the intent space. As you can see, this will also have to come up with a measure of similarity for these queries, which we will discuss in details in the later parts, basically. Yeah, before that, let's check a few points for the surface space similarity, because although it's very naive to say, but it has its goods in it, right? So it's, first of all, it's very precise because it's only doing semantic translations from one version to another. So it's in general more precise than and more explainable than the other approach. But although it has some decent coverage for a site like eBay, where it has a lot of variations of the query, but still it lacks in coverage as compared to the other approach. And although it's very precise, there are some very embarrassing false positives that will happen. Like I have listed a few of them here. One would be case not equal to cases. One is a chocolate, another is a music brand. And then the dress shirt and shirt dress, literally the same tokens written in different order mean different things. So yes, there are some guardrails to be put in because although this method is precise, without some guardrails, it will fall apart for these embarrassing cases. Guardrails could be things like looking at the distribution of the items that are shown for each one of those queries. And if you can see, the dress shirts will show very different items as compared to shirt dress. So it becomes evident there. Some cases, it's not so trivial, but in most cases, the items of these queries would reveal the problem. And we can extend this coverage to things like edit distances. So we can go for minor edit distances to take care of things like spelling mistakes and stuff like that, or variations of those. But we quickly learned that this will lead to the risk of false positives very quickly, and the guardrails will not be enough to stop them. So we can only do a few transformations safely and using the guardrails, and that's where it will be limited by coverage. And we'll see in the next approach, which is the post-search behavior approach. This one has much higher coverage because this will always find all the semantic ones that we found earlier, as long as they have enough user engagement. So this will never find a hypothetical query, which the other one can. But it will also have the risk of making more errors because this is in an intent space, right? So as you'll see in later parts, this has a measure of similarity, and how we use the measure of similarity will decide how tight or how loose that similarity space is. But generally, this is like a high reward thing. So we will get more similarity and more canonicalizations for queries, but it also comes with a greater risk. This has the benefit of looking beyond the query token. So it has the power of even doing semantic level similarity, and even using the whole query context to define the similarity. Like we can even use previous queries, requeries, and all those kinds of things to define the intent space. So this has more power of drawing similar queries, but it also has the risk of making more mistakes. And obviously, with any latent approach, we run into the problem of lesser explainability and black box approaches like embeddings and stuff like that. But in this case, we also have the problem that we have translated a binary problem, which is saying A equal to B, into a continuous space problem now, which is saying A is similar to B by a certain measure of similarity. Now, what measure of that similarity is actually could be used for a query is highly dependent on the downstream task and also on how we intend to draw the similarity space, like how we embed the similarities, we present the similarity space. So with this said, let's go over how we go about doing this task. So we can think of a query to be represented as a set of items. Now, which set of items we choose is dependent on, again, our target or the goal for this. So we can choose converted items, things which are bought on the site, or we could choose clicked items, and we could choose shown items. As we all know that each one of these come with a trade-off. If you choose converse items, then it would be a strong signal because people have spent money on that, but you would get very few of those signals. And if you choose impress items, which is on the other end of the spectrum, or you'd get the strength is almost negligible because it was the items that were shown to the user, but the signal is strong. It is present for each and every query that is done on the site. So arriving at a balance of this would be taking clicks, but depending on how our use case is, we can decide between clicks conversions as we need. So once we have this, we can think them of how we do representation for a sentence using the mean pooling of the words or weighted mean pooling or some kind of aggregate of the word tokens. We can do similarly the same thing. We think of the items as the entities of the query and do a mean pooling or a weighted mean pooling to come up with a vector representation for the query. But yeah, this also states that we have to have a vector for the items. So for that, we can use a pre-trained vector like a glove or fast text or BERT or whatever. Or we could fine tune one of these for our task using a co-click or co-purchased kind of target. We can fine tune these models, or we can even train a model from scratch. Depending on how much data you have, you can do any or one of them. So obviously now this brings us to the question, why would we, if we have an embedding model, why don't we just embed the query directly and use that as a representation? The response to that would be that the product titles are generally much more self-contained, especially when they are optimized for findability by the seller themselves. And they are generally longer than queries. So they have more context information. So they generally behave well in all of these well-known NLP tasks as compared to a query. So taking the representation of the items and aggregating them or averaging them out for the representation of the query has the representation is more robust as compared to using the queries directly themselves. So because the queries sometimes have some latent meaning in them, which are not presented in the text because they are obvious. Like when you say a dress, we don't say women's dress because it's women's. But if you look at the items, it's evident that they are all women. So you can infer those things by using the titles rather than using the query directly. Okay, so this is just an example of what I just went over. So this is iPhone 12 charging cable and Lightning to USB-C charging cable. As you can see, they have some text similarity, but most of them is at the semantic level. So we have to know the fact that the iPhone 12 uses Lightning and USB-C endpoints. So how we do this is basically we take the clicked items, we embed them using whatever embedding technique we want to achieve, and then we aggregate them just by mean pooling. And as you can see, the representations put them in a much closer in the embedding space for the two queries. Because the titles are similar to each other, so that information is being inferred for the queries themselves. So we'll go over some details of this approach. First of all, some of the challenges, like we stated earlier, like the first challenge is to say how similar is similar. And that question is hard to answer, and that depends on the representation, the data we used to compute the vectors, even the embedding model, and the application that we want to use it for. See, if you want to use it for exact similarity, our threshold has to be very strict, and it will also depend on the query. A query which has a lot of neighbors, the threshold will be much more dense as compared to a query which has very few neighbors. Like a query which is rarely represented on the site will have very few neighbors. So that threshold for that query will be much broader. So it's dependent on the query, the application, and the target that we have in mind. Like if you are optimizing for recall, then you just can't draw the threshold on similarity using the similarity value. You have to rely also on the recall of each of these queries and then see if the threshold makes sense. The other approach is, like I said, like any machine learning model, we have to evaluate the model. The offline evaluations are fine. Like when we create a training data, we will have a test data and it is good. Like we can validate the model's accuracy with that. But how would that pairs end up? Like once we have got the similarity score, how is the threshold behaving? So we can judge them in two ways. We can judge them as pairs. We can judge them as end-to-end result sets. If we judge them as pairs, it's independent of the rest of the search stack, but it also is dependent on biases. So for example, if I give you two pairs, one which is syntactically similar as compared to one which is semantically similar, you are most often likely to choose bias towards the syntactically similar, although the semantically similar query means exactly the same thing, because it's a trade-off, and it's human biases to prefer things which are similar in text as compared to which are similar in semantic space. And also you have to know the domain to make the semantic similarity, which is not always evident from human judges, especially when you crowdsource it. For end-to-end result, it's easier for the human judges, but it's difficult because to extract the effect of the whole search engine as compared to this just intent-based similarity. And like any other end task, we have to test it using an A/B test in an end-to-end application. And as you have already noticed, this approach will only work when we have a result set for a query. So this is representation of query is dependent on queries which have enough engagement. So it's mostly concentrated on the queries which are frequent enough on the site or are engaged enough on the site. So head and torso traffic of the site is basically covered. Not be able to go into tail without training a query only model. Yeah, so we'll summarize. So we went over what query understanding is, a very brief description, and which means basically inferring search intent from keywords. We also went over the spectrum of search intents, which are from coarse-grained categorization kind of things to fine-grained query equivalence kind of things. Query categorization improves relevance, especially in non-relevant sorts like price and time-based sorts. It also helps in navigation, trace representation, and analytics and other kind of aggregation tasks. Training query categorization is based on clicked items for a query, and recognizing query equivalence establishes a canonical representation, and we can come up with a query equivalence model by mean pooling of product vectors. With that, I would end today's session. If you have more questions, I will definitely take them at the end, and if it doesn't get answered in that duration, feel free to reach out to me. My email is there, my link is on the page, and yeah, feel free to connect anyways. We are also hiring for some positions that are open.
Thank you, Aritra, for that great talk. And so again, thanks to everybody who's been throwing questions into the chat. We will get to them soon after the third of our talks, which will be by Dominic Wessler. He's going to talk about autocomplete.
Thanks a lot. Hi, everybody. Just a second. Of course, made my mistake here. So you should see my screen now. Does it work? Yep, I see nodding. Thanks a lot. So thanks, Renee, and also Paul and Daniel for inviting me for a little talk. I will talk about autocomplete suggestions. My name is Dominic, and I'm a product manager in search in a little search team. I'm calling now from Zurich, Switzerland. And yeah, this will be a case that we had kind of, and I will guide you through it. More of that later. First, I will quickly talk about Digitech Coluxus, which is the company I work for. You might not know it, maybe you do. So please meet Digitech and Coluxus, which is together combined Switzerland's largest e-commerce retailer, and started in 2001. With on the left side there, digitech.ch, which then was, or still is actually, selling consumer electronics. In 2012, a new brand, Coluxus, was created, selling pretty much everything, which is actually the claim. And in 2016, then we have expanded into the German market with Coluxus.de. And 2018, we became a marketplace that helped extend the assortment to more than 3 million SKUs. So today, all in all, we have now 3 online shops in 2 countries and 4 languages and 11 physical stores. And as for search, so the SKUs you've seen, we have 500,000 searches a day in average this year, and 1.8 billion in revenues in Swiss francs last year. So yeah, and moving on, we are continuously growing, of course, and keeping our lively community of users happy. And now I will start the cause for the case. That is the question, what's the cause for this case? And in our case, qualitative user tests have indicated that our users were often unsure of how to formulate a search query. And certainly that was really bad news for our search box and also for our search team, because we were deeply hurt seeing our users struggling with this crucial step of their discovery journey, not knowing what to type. So why was that? At the time, our search box displayed many instant results. So please excuse the German screenshots. I didn't find any other ones from that from that point of time, but maybe you see the problem already. So we showed many instant results as the user typed, consisting of, you see that on the left side, you see many of them where we showed the brands that were already matching. We showed categories or so-called topics, which is a bigger cluster of categories, even contents from the magazine, which is pretty big in our case, like reviews, product reviews, tests, trending articles about something. And on the right side, you also see for this iPhone query, there's also product hits and quite many of it at the end. So we thought this was, anyways, too many results. It put a high cognitive load on the user to find relevant results. Just by looking at this, you have to read a lot also. And especially cumbersome on mobile phones, small screens generally, because the user has to also type the whole query. And yeah, that's not so easy to do with the small phones. And certainly the amount of information on small screens is also very challenging. So yeah, generally speaking, I think we could say that we didn't have autocomplete suggestions and that users kind of expect that also. We were already heading into this direction, of course, clearly. So I'll walk through our case that now focuses on how we could assist users in formulating better queries. And the main point is, of course, by enhancing the search box with these autocomplete suggestions. And another, I think, quite crucial point in my talk here is how we try to keep that solution simple, because yeah, we are a small team and we wanted to keep it also maintainable. Yeah, so simplicity and being also quick was quite important for us. So what did we do? Talking about being quick and lazy, maybe. First, we thought, let's help the users not to having to formulate the query at all. So yeah, you also see that we have, of course, redesigned this whole search box. Crucial part here is that we show now recent searches to the left and on the right side, recently visited products as a shortcut for like revisits or like multi-session visits. So there are still some learnings in there. Of course, it's not tackling autocomplete suggestions at all, but as a little key takeaway here, recently visited products here, the clicks have the highest conversion rates compared to all the other clicks within the search box. So that can lead to a lot of hypotheses, which I will not cover here. And yes, it's almost unrelated to our initial question, of course, but yeah, I will come to that now. So how to help formulating better queries. The big redesign now, when you type, was supposed to reduce the cognitive load for the user. So don't make me think. That was, of course, an important thing. So from the UX part of it, I think when it comes to query understanding, yeah, you should help the user by not trying to defocus him or her. And so we chose to show the new autocomplete suggestions on the left side mixed with still some instant results for products. But I will, of course, focus now on the suggestions, which naturally, then we all know it, I guess, somehow should help to assist and guide to better queries, also help with domain terminology, inspire about possible types of queries, and a lot more, I guess. I will now focus on how we created these and walk through the different parts of our solution, mostly on a conceptual level. Please don't hesitate to ask also technical questions if you have any, since I might have spotted some of my colleagues, co-workers here in the chat who might be able to help then if I can't. Worst case, we can discuss it later. So we chose to, on a high level, to create those autocomplete suggestions from popular and well-performing searches from the past. So that is kind of the umbrella for this whole. So now you see it already all in place, but step one, a big one, generate and retrieve them. So we chose to extract the queries from the query logs. And since we didn't have a dedicated query log, we just tapped into our Google Analytics tracking data, which sounded wrong kind of, but proved to be pretty okay. These queries are then fed into a separate suggestion index, of course, another huge design decision kind of. So to have a separate index for that, there's many other ways you could try. We went for the index one. So from there, we can retrieve the suggestions and show them directly in the search box. So it's done. But the suggestions, they would probably not look like the ones that I show here, at least not that readable and not that nice, although they're not really nice. But first thing we have to do is we have to filter some of the really bad queries, like very long ones, ones that are never clicked and show no results. Of course, we don't want to suggest any of that. The second part is that now we still see before the second part, we still see some queries there like TV Samsung, Samsung TVs and so on that we still don't really like. So the second part is then that we cluster them. This is all like pre-processing now still. We cluster spelling variation. So thanks Aritra for introducing the concept already. The one that has goods and also the bads. So surface query similarity is exactly what we do. Order of words, plural, singulars, a lot of stemming and so on involved, which I won't cover in any more detail here. So now we apply those and we get then actually rid of 3 of those TV Samsung TVs and so on, and also the typo there. And then the next thing we need to do is we want to prefix match. So that was our decision to do prefix match only while typing, because we wanted to ensure some better readability and yeah, to some extent also avoid irrelevancy in which you can see maybe in this example. Fireman Sam might not be the most relevant one, maybe it is, but I guess it's not. And so we do that. Finally, we get rid of Fireman Sam as well, and then it looks like that. Much better than before. Heavily Samsung here, but this is just what comes out then using our query logs. So now we have all 3 parts here in place in an MVP, and this allows for heavy tuning if you want, or if we want. And that leaves us with the question then still, how are we going to rank them? Because that's not yet really solved here. And for us, meaningful ranking then of those suggestions was about the trade-off between popularity and performance. So, I mean, you could also rank them in any other way, from random to alphabetically to, for us, it was popularity versus performance. And finding the metrics for popularity was pretty simple. You see the yellow. So we said, well, that must be the number of searches. When it comes to performance, there we found many more choices like clicks, click-through rates, conversion rates, revenues, and so forth. And now our approach was to simply take the sum of clicks over time, which in fact is the sum of click-through rate times the number of searches over time. So it shows a bit now the mix of our approach between popularity and performance. So we take 2 examples. We have the iPhone example on the left side that has many searches, many clicks, and then compare it to the iPhone 12 on the right side. These are actual, I actually made these up, so don't worry if you think it's completely wrong. But key point here is that the iPhone 12 query seems to be less popular and also less clicked in absolute numbers, but clearly has a higher click-through rate. So one could argue that this should be weighed more, but our approach clearly favors on the left one, so the iPhone would show higher. So again, generally speaking, this approach puts more weight on popularity than on performance. And yeah, well, counting clicks was fairly simple to implement, but as simple as it was, it of course has also some shortcomings, as I just said. So we thought we'd solve the ranking by just taking the sum of clicks, and we were quite happy about having found a simple solution, but popularity kind of appeared to be trickier than first assumed. So we wanted to react to trends and seasonal searches as well. And here we have an example of 3 queries with the green one, iPhone 12, as being the trend kind of coming up at some point. And we assume, so in week 9, let's say we're there now, we would have, with our approach, iPhone 8 as the sum of clicks model dictates as the top ranked query, then iPhone, and then iPhone 12 in the end. And obviously we wanted to have the iPhone 12 come up first. So the question then we were left with was, how sensitively should we react to trends? How to balance different types of popularities. So not sure if there is a straight answer to this, and I guess it depends. What we did was, again, try to be pragmatic about it, of course, as always, and we just tried to penalize past clicks with some exponential decay model over time, kind of. So we just added a weight to the clicks that we are counting. It's pretty simple, actually. And yeah, I think it's very simple and effective. The beauty of it lies in its simplicity, I think, for now. But think about it a little bit more. It also has its shortcomings, like it doesn't really deal well with less popular but relatively steep trends. Here, the blue one you see. And also if they end abruptly, I guess there are some examples of it. I guess it also really depends on your search and what your users want and how seasonal it is and so on. But for now we have a model, and we can also experiment now with this. So just a quick recap, we have all the ingredients in place, query logs, filter, then we cluster it, rank them, feed it to the index, and then we retrieve it. The retrieval, of course, you can do probably a lot of stuff. You can also plug in a lot of trained models to try to figure out context and stuff like that. But that's not part of my talk now. It's just having those 4 parts that are ready to do that if you would want to. And to sum it up, kind of, I would just quickly would like to show what I was talking about, how it looks like today. And I'm not gonna really comment on that. But of course, you probably see that there is also now these categories, mobile phone covers there. I did not talk about it at all, and we have added it at a later stage for some reason, and it's also ready for more experimentation, I guess. Has its pros and cons, like everything does. So, case closed, but what did we learn? One important conclusion was, of course, we did a lot of A/B testing, and again, quickly show the A versus the B, old versus new, and some of the business metrics we clearly saw have higher. The CTR, I mean, was pretty much higher on the products on the search results page. So we there saw a 20% change after the release. That was, for us, was huge, of course. And we also went down in the 0 result rates and exit rates. And on another note, we also then shifted, of course, a lot of traffic because before we showed kind of links to other pages a lot. So now we go all to SERP once you click a suggestion. So if you want to do that, your SERP better be ready for it, because it will get much more traffic. One thing, this was a pretty huge redesign also, which made testing and especially interpreting the results very hard. So that's a key learning for us that could have done much better, I guess, I don't know how right now, but this was a problem because it was hard to compare these 2 huge visual differences. on a kind of a project level, or like what did we learn from how we did it and so on. So we are happy with the results, kind of, or not kind of, we are, because it's very simple and yet effective. It was for us really swift, because quick to develop. We were very quickly ready with a viable release candidates. And by quickly, I mean, it's in the order of several sprints of 2 weeks each. Of course, it's not ready to deploy, but we had suggestions fairly quickly. And it was also lean. Again, want to like underline the start with using Google Analytics. You might think it's a bit unorthodox, but it's proved itself as because it was there and we just had it. It was ready and we could just extract from it. That was awesome. Of course, now we have a better solution for tracking and query logs, but this was very great. Yeah, and of course, what worked for us might not work for you. This was just our case. And yeah, I think with this, I would close my talk. Thanks a lot for listening. And I am happy to, or I guess we are happy to take questions now. And I think we are through with the slides for today. Well done.
Thank you, Dominic. And thank you, Andreia and Aritra, for participating in this panel. I see that questions are coming in through the chat, and I will give those. But first, I do want to exercise my one privilege as the host to ask a question to all three of you, which we'll do starting for Andreia, which is, how do you decide, and I know this is contentious, but whether a search challenge should be addressed as a query understanding issue, as a ranking issue, or something else? What's kind of the framework you use for this?
That's a very good question. So actually, as I think I said already, we are currently growing a lot. So in the past, we were just one search team. So it wasn't really like we had to decide how to categorize a problem, but it was more like how to tackle it and how to find a solution for it. But actually, so I think my opinion would be you can always look at problems from different angles and solve them in different ways. So I can either say I try to understand the query and adjust the ranking to represent what I think the meaning is, but I can also say I try to understand the query and adjust the selection, for example, for what is shown to the customer. So it probably depends on what kind of resources and what kind of knowledge is in the team, what is the best approach for solving that problem.
Aritra?
I think, yeah, we are a little bigger in structure. So yeah, we do have teams which are like query understanding separated from like as a sub team of search, but other than ranking. So yeah, we would start like if we'd see where the problem is the easiest to solve. It always starts with a customer problem, right? So if it's like we can always ideally solve this problem fixing it at any point of the stack, but we would start with where it is the easiest to solve, like where the problems has actually begun. Like if you have a problem which is clearly an understanding problem, if we had a signal from understanding which said that this is the signal, this is what this query actually meant, and which would have made the task easier for ranking, or say it's a ranking problem, or it was a navigational problem, then we started with that. But if it is more of that we have given the signals but ranking couldn't really use it, then we would go with ranking or retrieval to solve the problem. So depending on where it is easiest to solve would be where I would pick it. Yeah.
Dominic?
Sorry, I wasn't paying attention. I'm really sorry.
No worries. Just curious. I mean, when you think, and maybe in the context of autocomplete, like when is the problem the query versus when is it ranking? How do you kind of triage where to solve problems in search, given the complexity of the stack?
Yeah, I think it's. I mean, ideally the earliest possible, right? Because I mean, you need kind of some idea of a signal or something. I guess the problem always for us was, we we discussed that kind of quite a lot, how we have this idea of being able to pre-process as much as possible by inferring some stuff that we then get from the query out and can use in some way. We don't do much of it yet, but it's kind of a thought in our heads. And yeah, we just haven't been experimenting kind of with it yet. But I think it's a very interesting topic.
Fair enough.
I can't say where, what, really.
No, that's good. So what I'm going to do now is attempt to round robin questions that have come up in the chat to each of the panelists in turn. And by the way, you know, the questions are really directed towards each of you separately, but if you have strong opinions, chime in before we get to the next one. So first, for Andreia, the question was from Shrikant. Are there any weights distributed to the events inside the funnel? Because product clicks are direct indication of relevance that are, I guess, not as product clicks are direct indication of relevance, and then add to cart isn't quite, or something like that. Perhaps you can understand how the funnel works here.
Yeah, I think so. So I mean, I think you can apply weights actually in both directions. So you can either say, okay, the click is maybe more connected to the query, so it's more important, but also the order is a stronger relevance signal. So you say that one is more important and it's also less frequent. And so I think it also depends on what kind of, so if you use relative numbers, I don't think you need to scale them somehow. I mean, if you say I want to improve more on my order numbers, then probably you need to put a higher weight on that. Or if you just want to increase your click numbers, you need to put a higher weight on that. But if the numbers in themselves are relative, you don't need to put them on the same level, kind of. But if you use absolute numbers, I think it certainly makes sense, because you will have many more clicks than you have add to carts or orders or stuff like that. And actually, we are not yet at the point where we combine different signals. So we want to do that in the future, and we probably will do experiments to find out how to get the weights right. But yeah, so right now we are still trying to find out which part of the funnel is best for the relevance question.
Yeah, no, it's interesting. There's kind of multiple objectives, and figuring out whether you should combine them by weights or isolate them or even implement it as multi-objective optimization is a very challenging one in the space.
Yeah.
So, okay. So, I speaking multi-objective optimization, I will try to diversify the questioners. But another question for Shrikant this up to Aritra, which is, the text classification task for the product category prediction will suffer from dominant classes that contain 1,000 products over minority ones that contain 100 products. How do we overcome this limitation?
Yeah, so that's true, but generally this will depend on the category hierarchy, right? So if you remember from the presentation, we were using the hierarchy to roll up the categories. So when we create the training labels, if we don't have enough evidence for a certain category, we generally don't tend to use that as a label. We generally tend to pull it up till we can get enough evidence. So the minority class, yes, we will not be very accurate in the prediction in that case, but we will most likely give a superset of the items that you predict. But the minority class will basically not get the prediction. We will try to roll it up till we find enough evidence for that query. So yeah, that's how I would go about handling this problem. But yeah, it still suffers from the fact that only a few dominant classes will appear because of how we roll it up. But yeah, that's the nature of the problem, because the minority ones really don't have that signal to train anything on them right now.
Yeah, also, I think I just the question right. I mean, the issue is not necessarily about minority of inventory, because it's a demand signal, right? It's not just doing counts, right? It's doing it's counting clicks or other kinds of engagements. So which might address it somewhat, but Yeah.
Okay. Yeah. I answered it kind of thinking it was demand signals, like categories which have less demand signals than 100 and the categories which have 1,000 demand signals. And because we were using it only for deriving it out of demand. Yeah.
Oh, very cool. So the question Dimitri has for Dominic, can you integrate filters into the suggestion logic? Something like more popular filter values alongside of the keyword phrases suggested, especially if we know nothing about the user.
Yes, a great question. I think we don't do it. When I think about it, I guess this could be a pre-processing thing for certain. I mean, we try to extract meaningful information from the query logs. And so that's for instance the queries, and I mean you could also track, you could also extract what happened after those queries. So if, for instance, you see that some very popular filters were applied, I guess you could certainly try to suggest the query that also adds that kind of value of this option, like gray or whatever. So yes, a great question, and I think should be tried.
I'm curious, actually, from an interface perspective, I know that a lot of sites use autocomplete with filters, while others, kind of the filters become built in to the searches as text. And if you've seen any difference in the kind of experiences there.
Okay.
But I'll move on to the question. So Ben asks, Andreia, could you elaborate more why the Bayesian approach is not scalable in your case? Is there a heavy computing issue?
I'm actually not quite sure if I understand the question correctly, because we are actually using the Bayesian approach to get a better estimation of the click probabilities, but maybe I didn't get that right.
Well, maybe he can add more details in the chat. We'll get back.
Yeah.
So, Dimitri asks to Aritra, if you go for vector search, how do you incorporate filters in the eBay interface as part of the search process? Are you pre-filtering and then running an approximate nearest neighbor? Or is there some way to embed filters along with the text portion of the query? And it's not clear to me whether this is specifically about the query similarity part or the or categorization.
Yeah, okay. I will try to answer it for the similarity, but yeah, if it's not for that, please feel free to write it on the chat. I'll try to answer it better. But yeah, I think for the similarity, you can do it both ways, and you can embed it into the query itself, or you can pre-filter to the embedding. You can pre-filter the embedding space to the filter that you have already applied and try that. I think what I learned, the embedding it in along with the text itself performs better, if not like at least if not substantially better than filtering it, because if you think of the filters, they have some inherent information stored in them, be it category filters or be it aspect-based filters or properties-based filters of the items. And some of them times they are overlapping. So if you try to make the space smaller first and then search in it, you are already excluding all the results which might be in similar intent space because of the overlap of the properties, but you gain that when you embed them along with the text. So that would be my suggestion for that. That I according to my experiments, I think adding it is better than pre-filtering it.
Yeah, I'll just say, despite my my track record in history as far as liking faceted search and the use of structured data, there is something to be said for not pre-filtering, because that could potentially expose limitations that are unintended. So that makes a lot of sense. A question for Dominic: Do you show this is from Arna. Do you show the scene products on mobile devices as well? I'm asking due to the very limited space there.
Yes, we do. Well, I mean, keep in mind that we show it only once you kind of open this instant search box. So once you start typing, it will all be full of hits and suggestions, of course, so only on the first click when it's empty. And yes, then we do show it. We show the recent searches and the recently visited products. So please try.
Excellent. Matthias asks Andreia, so you mentioned keyword search versus browsing through navigational elements. Do you consider someone searching for couch the same as someone who clicks on the furniture category and then on the couch subcategory? Or do you treat them differently with different features or models for the resulting product lists? Should navigational browsing be considered a special form of search? This is actually a very hot question. I'm curious of your perspective.
Yeah, it's a very good question. So actually, I think we will be treating them differently, because if you don't do that, you would need some kind of matching to find out which navigational query is similar to a search query. So I think, at least for the beginning, because right now we don't rank with models on the product lists, on the navigational results. But if we start doing that, I think we will start with a different model and probably try to find out if it will behave differently. So that will be the key question for the first experiments for me. And if it doesn't, maybe we can find a way to use similar models for similar navigational and search query results.
I'd like to add some question, like a follow-up question on this, because this really is also for us a little bit of a hot question that we have been discussing also. And so navigational, so you end up using the navigation on the category called couch, whatever, and you search for couch. What is there the same and what is not? And what if, there's also what if you directly enter on this category couch coming from, let's say, Google, where you certainly searched for couch and then you got this hit. So what is the difference there? I mean, is it like 3 different things, or should it be all the same or not?
Yeah, it's certainly very, very interesting to look at the differences, if people even behave differently, right? So I don't really have an answer to that. So it's something we will certainly look into if we try to implement learning to rank on the search result page first, and then go for the navigational result pages. And then we will probably come back next year at MICES and present our results.
Yeah, I can say that one of the challenges.
Sorry, I think my internet connection is.
Yeah, you're back though. Yeah, but precisely that the navigational pages are often the SEO pages. They're ones that attract those clicks, which has it's great that you get traffic, but often the traffic that is coming in, for example, from a Google search versus for the site search does have very different characteristics, even if the topical intent is the same. For example, the purchase propensity may be much different. That certainly wreaks lots of havoc in my experience on comparing experiences when it's not necessarily comparing into the same sets of users. It requires a lot of care. So I will say, Jönte, I know you're curious about the numbers for maybe, and I'll deflect this one from Aritra, since I know he can't answer things that metrics from public company, but I will take the liberty to say I got to see successful experiments that improved conversion using embeddings as opposed to conventional approaches. But perhaps I can reframe the question to be a little less problematic. Richard, what do you see as the advantages of using embeddings for doing things like similarity and recovery, as opposed to, for example, these conventional approaches like synonyms?
First, one advantage I say is synonyms are hard to contextualize, because synonyms are they are word specific, right? So if you come up with a whole query and then you want to come up with synonyms, that's much harder. And sometimes the problem is not about finding synonyms. It's about finding a rephrasing of the query itself, which are even harder with synonyms. So I think the vector-based approach kind of hides this thing. It's working on the latent space. It has its problem of the black box nature, because you don't know what it has actually understood of it, but it generally takes care of using the correct synonyms based on the context of the query. So if I think of it like from my experiments and from what I've seen, it does learn most of the synonyms anyways, and it gets the advantage of the synonyms, but it also has the advantage of using it in the right context. It only applies the synonyms to the right context as compared to textual syntactic synonym based approaches. So that I would say is the major advantage of doing a recovery using latent space as compared to old or traditional, I would say, a synonym based approach.
That's excellent. Totally agree. Question for Dominic. So you talked about clusters in the context of suggestions. How do you define the representative term in a cluster?
Yeah,
this is coming from Marcel.
Thanks for asking this. Well, it's this what Aritra actually introduced the concept of surface query similarity. So we do some like word tricks, let's say. So stemming is heavily stemmed things end up in our suggestions index. In the end, order of words is an important thing. So you get TV Samsung equals Samsung TV, and yes, it comes with all the potentially embarrassing problems that Aritra also thankfully pointed out. And stop words are a thing. So we try to get like a bit of the noise out. And as I see it, it's the normalization process that we do with a lot of, I think, of information that we have also in the documents that we want to retrieve. So then we cluster them, and then we add together, of course, the clicks of the both, so that we can show if somebody is searching for TV Samsung. So we show the TV Samsung one that is clustered to Samsung TV that might be much larger, but then we can show it also on the top because we say it's the same. But it still looks like we still like use your phrasing like the users.
Mm-hmm. So Surya has a question for me, although I think everybody should feel free to chime in. This is a question. With the rise of neural information retrieval, do we still need query understanding? And he notes that I have a blog post on this, so I was hoping for more discussion. So obviously I'm extremely biased on this, but I would say yes. And I think the point that Surya is making is, which is also come up in Andreia's talk perhaps as well, which is that can't we just do this end to end? We need to really separate out query understanding. So my argument for that we need query understanding separately, first as a practical matter, that because even with neural retrieval, scoring and deciding how to look at candidates can be quite expensive. So I think it's quite important to say, look, the very first level of things you're going to do is to come up with a representation of the intent that will drive the retrieval, which then has to decide on a reasonable number of candidates, which then gets scored and ranked or possibly even sorted by things like price. So I think it makes sense to think of this in a pipeline where understanding the query happens first. But the other thing is that imagine a situation where you do a search and we don't have what you're looking for. And in that situation, it's still very important to understand what you're looking for so we can negotiate with you the way we might have, have something else instead. And I think that if you reduce that to saying, how well do results score relative to your intent, it is much more difficult to have that kind of a conversation with the user, to have that interaction without a clear representation. So again, very biased, but yes, I do think we still need query understanding, but invite the three of you to share your perspectives on this and certainly to argue with me.
Yeah, I think I agree with you on this, but for a little different reason, would be that if we try to build up a whole system, end-to-end system with only a neural model, the amount of memory we have to build into that model would be extremely large. And the more memory we build into a model, the lower its chance of generalizing. So I would say that query understanding is necessary because we would like to separate the different components of this memory aspects from each other. So you keep each of these smaller sections can only deal with a small set of problems, and then they could feed into a bigger problem for solving the larger ranking retrieval problem. So that way I would say, yeah, neural models are great, but I would keep them small. I would keep them task specific rather than them generalizing on like an end-to-end problem. So that would be my reason why I would still keep query understanding there, because each of these small models is representing one query understanding aspect.
Yeah, we also say something there, which is actually not much. I agree a bit from my feeling to what Aritra also now said. Although, I mean, as for credibility, me and also our search team is not yet really experienced with using that kind of stuff. We do learn to rank, and that's that so far. And yeah, I think nothing more to add here.
So in my opinion, it also makes sense so I think what I agree with what was said before. From my data science point of view, I would also say, I hope you can understand me, but I will also say that it's very, very hard, all the issues you have. And that would also be a point for me that speaks for having a query understanding, some kind of query understanding in the beginning to decide or to create smaller models that can do particular tasks, because I think it will be very, very hard to build one neural model that will solve all your problems.
Excellent. So some more questions here. Hussein asks, and anyone feel free to take this, do you have any recommendations on how to deal with homonyms? That is, two words, two different words that are spelled the same way, but have different meanings in query understanding.
I think I would deflect that to the search results page with did you mean this or that, and then move on. I think I wouldn't even try to deal with it in the first place. It sounds too complicated to me.
So let me see other questions that are in here. So I'm now going to take, there aren't that many in the chat, so I'll take them in the order I see them. So Matthias asks Dominic too, how do you come up with the product suggestions in Autocomplete? How do the product suggestions perform relative to search rates? So I guess this is a question of instant results versus Autocomplete.
Thanks for that question. I was hoping for it not to come.
Sorry.
Since it was very, I mean, the discussion to have the mix of suggestions and product instant results, I mean, was also driven by a lot of opinions that we had coming from kind of 95% or 100% instant search only that showed kind of everything. So we wanted to make it smaller, and then we were left, what we left were the product results. So it had a bit of a trade-off, I guess, also in it. I mean, as to how we create them, I honestly can't say technically really how we retrieve them and so on. I think, I mean, there is no like okay, wait, maybe I'm not sure. Maybe there is some pre-processing there too. I'm not 100% sure. I would need to take this question to the team. And as to their performance, I was trying now just to look up some real numbers in clicks. And I mean, they're not, I think generally you can say that we don't see a lot of clicks. So they're clicked like maybe 3-4 times less than the suggestions, but still they are clicked a lot, and the conversion rates on those clicks, as a simple measure of when they start with that, is much higher. So that also seems to have the same I have the same hypothesis a little bit that I have with the recently visited products. So like you come back and then you it's kind of a shortcut. You know you're more at the end of the journey than in the beginning of a journey, I believe, of the discovery journey, or maybe the purchase intent is much stronger. Stuff like that would need to be researched on a bit more. I don't have much at hand right now than what we track.
So Renee has a question, a great question for everyone, which is, it seems that we try to understand queries based on observing users and by statistical models to interpret their behavior. What's your take on more qualitative research? And to what degree do you find an overlap between user experience research and statistical modeling? So who'd like to try this one?
Maybe I think I already gave a sneak peek on that. So we are quite fond of doing a combination of those, and we are currently implementing something to get more qualitative feedback in our experiments. And there's also another team on AutoDE who did some experiments on the search experience, and they also did it with qualitative research, and they just asked people to search for something, then describe how easy they found it to find whatever they could be looking for. And actually, it's quite interesting how you can expand what you learn just from looking at click logs and then adding that more descriptive feedback to that. So I think it is, so you always have like theories in your head about how users behave and why they do things you see in the click logs. But if you have this UX experiments added to that, you can actually see if your theories are correct or if you obviously are very biased through your job. That I think is very often the case.
I'd like, Richard, go ahead.
Yeah, I would add to a point there. I think I think it has its own values. It's generally addition to what we do with clicks. I think Andreia summarized it like very well. That once the click logs are good in come up with a bunch of predictive behaviors, but then the UX research is basically just to enforce on which one of these predicted behaviors is actually more valid. Like it's a more descriptive way of saying what the user actually did. So yeah, I think that's a very important point for overlapping UX research with statistical models. I think that's the biggest overlap.
I'd like to add sort of two thoughts. One is that what I found is that usability research can bring two things that quantitative research usually cannot. One is things that are really just inside of the user's head, but don't necessarily show up in an obvious way in behavior. So for example, you might see that somebody clicks or doesn't click. That's great. But you don't necessarily know that when they don't click, they were offended. Like they were like, it was a very negative experience, because you don't not click harder than not clicking, right? A 0 is a 0. And that's something that might be extremely obvious when you talk to people, or maybe even something that's a little bit, I don't trust the site, the things that are in their heads. It actually makes you think of the first talk that Angel gave this morning. But the other is that users can tell you so much more than you'll get necessarily from just a behavior trail. So it's great for hypothesis generation to build a model of what might be going wrong. Terrible for figuring out the exact number of times it goes wrong, because you're not going to be able to do this at scale. But if you can generate hypotheses, operationalize them, and then use those to actually quantify them and look for them, I think that process works. This is at least my experience in using these both. And I do think it's important to have a combination of this qualitative usability research with quantitative analysis.
Yeah, I think I would like to, I mean, I totally agree with what you said, Daniel. We are also, like Andrea said, we are also pretty fond of UX research. And like you said, Daniel, we also see that, of course, it scales a bit differently than taking just data and, and create hypotheses out of that. What I find always when we watch a video of a customer doing some task or given a question using our product, it's much more messy than we ever anticipate. How they try to solve it, in like messy in a way of all the different ways they come up with, and there is no like their user, so there is like a gazillions of them, and they're all in different contexts, and this is just really hard. I think for me, it's always very enlightening to see it, because it shows also, yeah, it's all an approximation, right? If we take the data and we try to make stuff very simple, so it works, but it's just not.
Yeah. So we lost Andreia to a thunderstorm, but I hope we could keep this going. Shrikant has a question for Aritra. For product category prediction, you have a query and a product title for getting the context. Are these two features enough to direct the prediction to an intended category? If not, what else can be considered as a feature? I'm not sure that you follow the logic, so maybe you just review the basic.
Yeah, I think we don't have the product title also. So it's basically, we have the product title to divide when we are collecting the training data. We don't have it at the training time. Training time is basically the query text and the category. And from my experience, yes, it's more enough for us to predict categories. Am I correct? The 100% of the times? No, no machine learning model is, but it's at least it's enough to basically say what would be the category of this query in a broad level, if not at a very granular level. Like if I can at least say that given a query that this would be a vehicle query, a motors query or something like that. If not, I'm able to say that this is vehicles with so-and-so year and so-and-so model. I might not be able to be accurate. Like the more granular I go, more signals I will require. But on a broad level, to say if my categorization task is to only find broad categories or semi broad categories, not very specific ones, I think the query signal itself is more than enough.
So Surya has a question, which I apologize for not getting to earlier. Again, directed to everyone. In query understanding, you're generating a lot of signals. Query classification, named entity recognition, results from query expansion, etc. How do you go about combining these signals in a principled manner to retrieve the most relevant results? And maybe Andreia, if you want to kick that one off, because I think it's relevant to some of the things you described in your talk.
So for us, it would be using them as features for our ranking model, first of all. So if you get the I don't know, the expanded query, or if you get the intent behind the query that you classified, and then you can add them into your model as features, you can do a much more specified ranking. Or even, like I think we mentioned that before, you could think about probably I will need a different ranking model for different query intents, right? So I could train different models on those queries where users behave differently and use them as dividing points to where to go next for my, for example, for my ranking model.
Yeah, so essentially, like I was thinking of like a tree, a model selection or a tree of models.
Yeah.
Yeah, I would say, yeah, the principled manner to retrieve the most relevant result is a hard problem to solve, I would say. Blending is not easy when we have so many different signals which we want to put in. One way is, yeah, just throw all of them at the model and let the model figure out. But then that works for a lot for a lot of cases, but in some cases it's harder than that for the model to even figure out which signals to use for what kind of task. So I would not say that we are like a perfect at this thing, but how we go about doing it is to see which part of the which section of the ranking or retrieval process lacks because of what. So if providing a classification signal of some kind helps in solving one set of the problem, you'd basically just do that for that small section and leave it out for everything else. So it's more of an hand-tuned blending in that case. So something like what Andreia said, that you pick and choose what you want to do, kind of a selection of which of these signals you will use for what. And that's about how we go about doing it. And the baseline for comparing it is basically throwing all signals to it and see how the model does. That would be my take at this.
So I have a question which has not come up, interestingly, despite this being a very international crowd, which is that I notice we're all speaking in English here, but our sites are not necessarily just in English language, and we're talking about query understanding. So to what extent can query understanding be language agnostic, or do you have to implement a separate stack for every language? I'm curious about your perspectives, especially because I know that the German and English in particular are quite different from a language perspective, despite both being Germanic. I don't know who wants to take this one.
I can start. Yeah, I would say it depends on what kind of problem you're solving, right? So if in some of the subtasks that we have, like some of the query understanding tasks are very language agnostic, and they can be translated from one language to other easily. But some of them are not. Like, for example, if we compare among German and English, compounding, decompounding is altogether a different thing between German and English. So if you have a language model which is used for query understanding for some kind of, even if it's a simple classification task, which we have used for English language, it might work well for maybe another language which has similar structure. But as long as the structure changes, we will basically have to have a separate stack. Like for German, we will have to have a separate stack. So I think it all depends on what problem we are solving and what are the two languages. Some models are very generic to like two languages, but then some are not. Like, for example, if you have to come up with a ranking challenge, which is using very little or no text signals as such, or it is using the text signal from a different model, that a different submodel is basically generating the text signal. That submodel might need to be different, but the ranking stack can just use whatever signals comes from there, and that would scale for all sites. I don't know. Yeah, I'd say it ends.
Yeah. No, Dominic, Andreia, I'm curious your perspectives, especially since you have probably more direct experience than anyone in this.
Well, I can say something about what I showed with the Autocomplete suggestions. I mean, clearly, also what Aritra just said, clearly the difference between the languages has a huge impact on the stemming part or the normalization part of decompounding. Order of words also behaves, of course, differently with many languages. When you have a more strict syntax, I'd say, then it's easier to do it. In English, when you switch this order of words, then you all of a sudden create new meaning and is a duplicate and so on. So that's not easy. So for us, I mean, it's clear you have to, it's not language agnostic there, or I guess almost nothing in this part is actually, I think. So you have to be careful.
Yeah, that's true. So actually, we don't really have different languages on our web shop, so it's not a problem that we are facing in our everyday work. But I would certainly agree with what Aritra said. So if we have some kind of ranking model that only uses very basic query features or that needs another model to feed it, then you can probably use that model for different languages, assuming that the people from probably different cultures behave in the same way. So that would be something that is probably also interesting, because it might be that people speaking different languages also look for different things in their search results. So yeah.
So Aritra points out, wait till you try Japanese. And indeed, I would say that I think that a lot of the assumptions here assume alphabetic languages, which within things like inflections and so forth, but certainly in Japanese or in Chinese languages, I think that breaks down. I'm just going to quickly say, Shrikant's asking when can we find the recorded sessions? Renee will follow up on that. Simon asks a question, which I think is close to my heart, which is, with common single word search terms, it can be difficult to understand what the user really wants. For example, shoes. Would you recommend treating such search terms differently than specific search terms? For example, showing a different UI.
Yeah, I would take that. Yeah, answer would be absolutely. That's yeah, and how we do about this is, again, some kind of, you have to understand when that query is basically generic. Sometimes it's single word search terms also mean that they are not, sometimes single word search terms are not generic, they are very narrow also. But when they are generic, you also have to get the variance that you can show. Like it's a much harder blending task at that point to show between the diversity that you actually want to represent. So yeah, showing a different UI experience is one thing, and what to put in that UI experience is a different set of problems. It's almost a browse query. You have to give them the options to navigate your site at that point.
Since someone has gone to spatial, please mute yourself on Zoom.
Thank you, Renee. So a question perhaps for everyone, which has come up. You know, we looked at different components of query understanding, but often, you know, we look at things kind of end to end, as far as, especially with A/B tests, in terms of improving the search experience. So how do you manage the questions of when to evaluate query understanding components like autocomplete or like synonyms or what have you on a component basis versus looking at it end to end? Do you do both? Do you do one or the other? What are the roles that they play? I'm curious, Dominic, maybe, you know, like starting like, you know, from autocomplete, right? I think you had metrics that were autocomplete specific, but also end to end as well. You know, how do you decide to and that mix of evaluation?
Yeah, I'm not sure if 100% got your question. So you mean how do we choose, for instance, how would we choose to do autocomplete or not compared to again?
Let me, like, do you say autocomplete is better because we looked at the quality of the autocomplete suggestions, or do you say autocomplete is better because, you know, people ended up finding something they wanted? And I mean, the answer could be both, but how do you do component-wise evaluation of the elements of the query understanding stack versus end to end?
Well, I can only try to cite kind of what the findings were in the A/B test, which was also hard to interpret. So we had to use very high level metrics, and which was, for instance, the conversion rates of the session. So you can't go any further out like that, I guess. It's really noisy. I mean, we looked at the click rates. So, I mean, for us, it was such a big change from guiding to queries. So we there was not much to question really, whether to do it or kind of not.
Yeah, I can take a stab at that. I think one way of deciding between when we can do human judgments and when we can do A/B tests is what is the outcome we expect. So if the outcome of our experiment was to evaluate something with most of a qualitatively, then I think human judgment is a better choice. Like if I go with my example, when we generate semantically similar pairs, if we just want to evaluate the pairs, if we want to say if A equal to B, do you think that's valid? We don't care about what it does to the end-to-end user, but we care about how that the task itself performs. I think human judgment is a better one. But when we want to evaluate some end-to-end task on the search site itself, I think A/B test is a better option because it will give the user feedback on a specific task using some experiments on it, basically, like using some where some of the subcomponents have actually altered. But if you have to just evaluate the subcomponents separately, I think human judgment is a better option.
So I actually maybe disagree a bit about that. So I think we would always, like, if you have something where you know the true answer, you can certainly do like an offline analyze your metrics from your training data if you're really sure that your training data represents the right thing. But I think it is always hard to estimate what your changes to one component in the end cause in the search system. I mean, if you know your search system so well that you can predict it, it's not a problem. But I feel like there are always, or you can always cause changes that you would predict before you test it on the customer. And then therefore, I think, or at least in our team, we always prefer the A/B test and not only rely on what we find offline for our model increasing in precision or whatever.
I think you raise a really good point there, and actually, you know, it's perhaps not even a conflict, right? It's exactly when there is a right answer. Like if I mean, I can speak to an experience I had with this, where we built a model that did a better job of classification in one place, and people downstream complained about the end-to-end metrics because they would have had to adjust to those models, but the classification task had a right answer, and it makes sense. On the other hand, if it's a subjective decision, perhaps, to say that you know, some upstream component is better, like we personalized better or something like that, it's like, well, no, I mean, that doesn't actually make sense, and you don't really get the feedback until the very end of the process. So I think you've nailed it right, which is that in order to judge the upstream things, you have to be able to have a notion of a right answer. I do think, though, when you do it, it's actually super valuable because then you can diagnose it at the source. So we only have a couple of minutes left, but Sebastian asked a question, which I'm glad he got, I think is a good one, which is, these are all great techniques, but the three of you represent quite large sites. So how much data do you need to be effective? I mean, and in particular, I'd say, what are the things you can do in your sense with sort of differing amounts of data? I know it's a broad question, but I think if each of you could sort of give your perspective on how data hungry these approaches are, that'd be a great way to wrap up this session. And to start with you, Andreia.
So I'm not 100% sure I got the question, but maybe I can, or at least for the judgments we create, we try to find a way to also incorporate smaller data sets and get a realistic answer from that. But actually we found that it's not really good enough. So we have to implement something to ensure the quality, even though we want to use as much data as we have. So it's always like a trade-off. How much data can you use and how sparse is the data in the end that you use? And do you really want to rely on what it tells you, right?
Yeah. By the way, I want to apologize to Sebastian that was not actually his question, but it was my question. So, but yes, his question, which I guess was the problems that bot traffic or other might have for models. So my apologies to him. You should feel free to answer as well, by the way. But it sounds like basically what your answer to my question was, yeah, it is quite data hungry. You need a fair amount of data to be effective.
Yeah.
Yeah. I'd answer both of them together. Most processes that we do are data hungry, and the problem of seeing how much data is enough is very process to process. So it's depending on the task that we are trying to solve. And general process would be to keep giving it data as long as I have data and the model needs data. So at some point you will run out of return to like data to return ratio, and that point will you can say that it has saturated on the complexity of the data. Like it has basically, but yeah, you also, if you give it more data, you also run into the problem of mugging up the whole problem. Like it will just memorize the whole thing and then it will not generalize. So there are some trade-offs on that, which are generally trade-off for any data science problem. But yeah, most of them are data hungry. And as for bots, yeah, we try to remove them. And so the traffic from bots are generally not considered for anything. There are multiple ways depending on the task. One of them would be bots don't buy anything. So generally that is a good signal to say that, yeah, if a guy is just searching, not buying anything, and he's searching for everything under the sun, yeah, bots do have ways of faking all of that. They generally fake their identities. They will come up with a different identifier each time and all those things. And they are hard to find. It's a constant battle between the unregistered bots and people who are processing the data. But yeah, we generally try to remove bots. And by the way, some bots are generally registered to the sites most of the time, so they are easy to remove. They don't fake themselves.
Yeah, so same here. We try to remove the bots. We are also suffering from that, especially recently when these new GPU graphic cards just were announced all this time and not being able to be delivered and stuff like that. So it kind of almost brought down our whole website. And yeah, as for the removal of the bots, so we try to remove them and not count them in any of the metrics, especially in like A/B tests, since you can have clusters of bots or like clusters of many searches in an A group, just because this one bot happens to end up in your group A, and that's not so good for your A/B test. And so for now, we have only very simple measures, like recognizing the searches, the patterns of the searches. They seem to have certain patterns in like when they come, in what time, and how many zero results they create, and what length they have, and how numeric they are, and stuff like that. So there is, I think, a lot of easy ways and a lot of harder ways we are, I think, soon are going to explore, because we are still suffering from the bots and can't detect all of them, or not enough.
Okay. Well, on that note, apologies for going a minute over, but thank you to the three of you and to the entire group for an excellent panel and discussion. Looking forward to all the discussion this generates after the conference. So see you all in about 8 minutes for the lightning talks.
Yeah, so before everyone runs away, thank you very much for 2 hours of a very interesting panel discussion.